It's not drawn very well, characteristic impedance. And your feed here would be coming in with a source like this. All right, that's how you'd feed it. You all follow me? Now, this will provide the DC bias, so that inductor has to be in series. Now, it could be either, there's two places you can locate it, obviously. You can locate it in series here, and then a capacitor here, but that requires you to be in the rotated Smith chart to use that configuration. You know, your ZL has to, when normalized, has to be inside the rotated. Y'all with me? And then you get a capacitor. That's one way. Or if you go admittance first, you go from inside the one circle, that's ZL, to YL inside the rotated, then you put a capacitor in. That's the point. Y'all with me? But DC bias means the inductor is in series and the capacitor is in parallel. That's all it means. And, you know, just let your brain think of it that way. Now, there are things, there's all sorts of tricks. There's the one thing bad about L-section matching, I must say this, it only works well at one frequency over a small bandwidth. Remember, as frequency changes, the characteristic impedance of the line doesn't change. Y'all left me on this? So then that L-section network doesn't look like it's impedance matching. As soon as you get outside, there's usually a center frequency and a bandwidth. There are things you can do to get wider band matching, but that's beyond the scope of this class. And is anybody going to take microwave? If you get taken microwave, they'll do that. They'll get into all the things. There's tricks. All right. Now, I gave you problems with S parameters. One of the problems I have, if it isn't going to be covered on the quiz, a lot of people don't even bother looking at it. S parameters, though, is something going to be on the final, and I'm going to cover. Do you have any questions about the impedance matching with L network or L section or anything like that? Anybody?
Could we just do one?
Which one?
Could we do one?
Yeah, that's great.
10 to 18?
Yeah, absolutely. And I'll say this too. This kind of stuff, there's so many ways to impedance match. This is one of many. But it's very useful because it's easy to do and there's not much real estate. By real estate, it means chip area used. Whenever you get into, you might have seen double stub tuning, some of you if you look online. You can look it online, they'll have all sorts of things with things called back valence, that's balanced stuff. This takes a large footprint or a wireless space, and also it's expensive relative to a couple of, an inductor and capacitor is cheap, you gotta admit that. All right, so this is 10, 18, right?
Yes.
And go ahead.
Design an L-section matching network to match a load ZL equals 100 minus J80 omega to a 50 ohm line.
Okay. Now this is the kind of thing you're going to see all the time. This will be on the quiz, this kind of a thing. You get a Z naught, and it's 50, did you say?
50 ohms.
All right, so they want an L-section network. Bless you.
Operating frequency 11.18 gigahertz. And then it has this DC biasing within them at the end.
All right, that just means inductor in series.
Yeah.
Everybody with me? Correct? You all understand it. The inductor's got to be in series. So now, I'm going to, let me do it right here. I'm going to put this Smith chart here as best I can. And all right, there's my rotated circle, and this is my R=1 circle. So all the time, the first step is always the same, and it is to find the value of ZL. Do y'all agree with this, class?
Yeah.
All right, so ZL is equal to capital ZL over Z naught. And for my case, that's going to be 2, right? Minus J 1.6. If you have the Smith chart, please watch this. Make sure you can locate this first thing. So if I have 2, well, if I look at this as R equal 1, 2 would be something like this. This would be the R equal 2 circle right here. You should be able to locate that. And minus J.1, that's this trajectory here. Now take a look at your Smith chart. So this would be the point. It would be point 1, it would be ZL. Can everybody find that? You have your Smith chart? Huh?
Wow, it'd be minus.
Oh, 1.6, 1.6, sorry. That's minus 1, sorry. This is 1.6, I'm so sorry. This is minus J 1.6. It's very close to straight north now. But it should be like this. And where the 2 intersect would be the first point at ZL. So it's going to be 2 minus J 1.6. Can you all locate that? In the far back, everybody? You good with that? All right, now, after that, you can see you're inside the 1 circle, right? Now, my next point's really important. If you add reactants plus or minus J, the only thing you do is shift the position you are on this trajectory. Do you all see this? No matter what you add, you can't get to the center. That's my point. You all see this, class? Did you have a question back there or no? No? Everybody with me on this? So what do you have to do? You go to the admittance domain. Admittance domain is going to be over here, and this is YL, which is 1 over ZL. Can you give me that? Anybody? If you got your calculator.
0.32 plus J.24.
0.32 plus J, 0. What?
324.
24. All right, now,
0.32.
is that what you got?
For the real part, 0.32.
I get 0.30, but
Could you guys do this and just confirm it? Just take 2 minus J, 1.61 over.
All right.
Huh?
There's like an in-between number, so I just kind of round.
You're going to have to, I mean, you know, what I would do is this. I would use your calculator, because that will work perfectly on a calculator.
and you can also just go draw a line straight through the center point, and then
Yeah,
that
but,
same thing?
but again, this is the thing. The minute you're looking at this distance and let it be equal to this distance, you follow me on this? If you took a compass, put it here, do this, you're still going to get the ink, or the lead's going to flatten. Now, you're going to get more and more variation. I'm just telling you this. All right? You're going to have to extract, you're going to have to interpolate things and try to get your best shot. What do you got?
Yeah.
0.3 plus J 0.24.
All right, so 0.3, you were right, brother. Plus J point what?
0.24.
All right. Okay, so that's why. Now, that's the admittance domain, right? Hear me. We're going to put a capacitor here. You all hear me? If we put a capacitor here, if we're inside that rotated circle, the next thing is going to be a series inductor. Almost guaranteed if we do it right, okay? Now, so here's a capacitor. I'm just going to show you what it's going to look like. The next thing we have to do, and please watch this. If you have any question, I'm going to try to be clear about this. Now we're here, and remember for a capacitor, if you have a capacitor, the capacitive reactance is simply minus J, I'll tell you, it's just 1 over J omega C, right? Does everybody agree with that? Just impedance of a capacitor, 1 over J omega C. Now, the normalized capacitive reactance is going to be 1 over J omega C Z naught. I'm doing it in steps to make absolutely certain there's nobody that doesn't understand the logic. You all with me? You normalize next. Now, if you have, that's the normalized impedance, the normalized admittance, which would be, I'll just call this small zc. Yc is going to be 1 over zc here, that's a C, and that would be J omega, right? C times Z naught. Does everybody agree with that? Everybody? Y'all follow me? In the back, you guys with me on this or not? I'm just making sure. Now, if that's the normalized capacitive admittance, right? You'll notice it's plus J. So where are we gonna move? If we wanna have a capacity, we're gonna move this way, right? This value, there's a trajectory where it's gonna be something like this. And that trajectory is really an orbit of 0.3 is the real part. You all see this. It's a huge circle with 0.3. And we wanna land, we wanna go from here, which is 0.2, to this point, which is 0.3. It's gonna have a real value of 0.3, but it's gonna have a different imaginary value. What is that imaginary value?
0.47.
Can you guys take a look at, make sure you can see this. Do you have a Smith chart there?
Yeah, it's on the ground.
I wanna-
Never mind.
I wanna make sure you can see it. Do you have one? Because I tell you, there are people that misinterpret this. Things that I assume you understand, you don't sometimes, and that's on me, but if I get you to do it, that way you can find out your mistake. Now, if you move from here to here, you should get a value of, and somebody said it was real part of what?
0.3.
No.
The real
Oh,
part.
yeah, sorry, 0.3 plus J what? I'm so sorry.
0.47.
0.47. Now take a look at yours. You might get something a little different. Do you have one to look at, guys?
Yeah.
Do you have one? Okay, can you see this? Good?
Yeah, 4647.
And that's where you're gonna always have that problem. So what's the difference between here and here? Well, this point is at 0.24. This point is at 0.47, right? So if we take 0.47 minus 0.24, put a J in front of it, we take J and we put 0.47 minus 0.24, right? That has to be equal to J omega C times Z naught, the normalized value of the capacitive admittance. Do you all agree with this? Andrew, do you see this or not? If you don't, let me try to help. You say, Brian?
Yeah.
Now, we have the frequency given. This will depend on frequency. And we have a characteristic impedance. So if we want, you can see the J's cancel. If we want the value of C, right? Just take a look at that. We have 0.47 minus 0.24. I'm on purpose leaving it that way. Then it's divided by omega, which is 2 pi, times that frequency. I'm just going to call it F, times Z naught, which is 50. So what value of C do you get? I bet you it's small.
0.065 picofarad.
Is that right? Anybody?
The solution he gave on Wentworth is wrong.
But calculate. I want to know what you get for this. Probably meant to say 1.118 gigahertz. That's high frequency.
He really screwed the pooch. He said Z load was 100 plus J80.
100 plus?
J80 in the solutions, but in the problem it was 100 minus
The
J80.
grad student might have done that. I'm being honest with you, I don't know, but I mean, things happen, especially when you're doing these problems late. What do you get for the C again? Anyone? Bradley? You doing it or not?
I'm on the next part. Hold on.
I just want to know what somebody else gets. I'm trying to get confirmation or denial.
I got like 0.06 times 10 to the negative 12.
Yeah, I got something like that.
All right, now at that level, a piece of wire in length probably changes more than that, just a small piece. We're talking about a capacitance that's not really feasible at this point. There's other ways to do this. Are you with me on this, class? It's so small. Now, one way you can get around that, but at this level, you know, capacitors in series, if they're all the same value, you divide by the number to find total capacitance, right? So you could take 10 capacitors of 0.6 picofarads, put them in series, and you would technically have 0.06 picofarads. Do y'all follow me? If they're in series? But the problem is the leads themselves will cause that to change significantly. There's all sorts of problems when you're at high frequencies, and that's high frequency. There are other ways to do this matching that are beyond this, but probably the easiest thing to do is stub tuning at this point. That's what I do, because the wavelength's so small. You're not gonna cost much as far as top, because what's the wavelength? Somebody just tell me the wavelength of that. 3 times 10 to the 8th over 11.18 times 10 to the 9th. That's gotta be millimeters. It's getting there. Not quite millimeters yet.
26.83 millimeters.
See, that's not a whole, that's a centimeter, a little over a centimeter. It's not bad. You can probably get that. You can do this with a stub tuner and get a very close value, a short circuit stub. But putting that in there, no, just too small. Anyway, that would be the right answer. Now, how do we get the inductor value? All right, we're here now. That's 0.3, guys. What do? We went from here to here. Now where do we go?
Go back to
Now we go to the impedance domain, right? We're in the admittance, we go to impedance. Do y'all agree, class?
Yeah.
So now I go back, just take 1 over that, and it better be about 1. 1 minus j something. What's the minus j something?
1.5.
Confirm that, someone.
Yeah, I got one.
Wait, so you take,
All right,
take 1 over,
say it, who's that?
what'd you take to get back to the?
All right, listen, everybody. I'm here, right? Now remember, that's the y domain, that's admittance. 1 over admittance is impedance. Just take that value, which is going to be 0.3 plus j 0.47. Can you all read this? Greg? Take 1 over that, you better get about 1. It's going to be 0.99 something. You'll never get, almost never get exactly 1. With me? And then it should have an imaginary part about 1.5, minus 1.5. You all with me? So we want to add an inductor in series to get rid of that, right? I'm being very, I know this seems too slow for some of you, but trust me, there are people that get confused in this, especially if you've been doing your project and not studying. You get confused. So how do I get rid of that? Think about it. I need an inductor plus J, an impedance inductor, right? So start with the impedance of an inductor, J omega L. I'm being as straightforward as I can. You all agree with that? Normalization is dividing by the characteristic impedance of the line. That's all it means. I divide that by Z naught. And now I have I have ZL. It's not the load, it's the inductor's impedance that's normalized, right? And then what do? I need that to be equal to 1.5, right? So when you add that on in series, it'll clobber the minus J 1.5. It'll get rid of it. Do you all agree? So I simply set J omega L over Z naught equal to J 1.5. I'm just showing you. Is everybody following the idea behind this and the reasoning? Everybody? Rather? And Andrew? And Greg? You good? Now, what does that give you for L? Well, L is going to be proportional to 1.5 times Z naught, right, which is 50, divided by 2 pi times F. And F is at 11.18 gigahertz, which is a high frequency. To me, it's a high frequency. I mean, I've worked. No, I take it back. I have not worked at 33 gigahertz, but I've been round worked that high frequency. When you get in that high frequency, you don't realize if you just stick your hand inside where the amplifiers are and stuff, and you have some way of measuring the resonance, if you beat it down, you'll hear. That's how bad it is. Go ahead.
Wait, is Z naught at 50 that you put 1.5 times 70? Is that?
Pardon me?
Are we multiplying 1.5 by Z naught?
Well, see this equation?
Yeah.
Do you agree with that?
Yeah.
Don't I have to multiply this side by Z naught to get L?
Yeah, but I'm saying Z naught 50. I thought Z naught was 50.
It's 50, sorry. Bradley, I'm sorry. I only can, right? I can't think. Y'all with me? That should have been Z. And what do you get for that? I don't know.
1.07 nanohenries.
Anybody else confirm?
Yes.
Correct.
Now, has his answer got either of those two? He messed up.
I
He's a
didn't
lot.
look at the book and I just looked at the solution and solved it before I looked at like the full solution, so I have his values. Didn't get they're completely wrong. Like his-
Okay, I hope you got that, guys. They're completely wrong.
Well, you did with the Z loads, you did plus J.
You did.
You just swap.
And it's probably one of those late night mistakes or when he's really tired. You guys got a question? Ask it.
Yeah, he was just confused on how, like, on the dividing, 1 by 0.3 plus J 0.47 to get to 1 minus J 1.5, I was just like.
Dividing,
He was
0.3.
confused on how you got there, but I was just.
oh, it's just 1 over y.
Yeah.
That's all it is. And look, you do it any way you want. It's true that this length is this length and that length is that length. But to me, it's easier if you got an actual value here for ZL and you want to go here, take 1 over it. There's no error as far as your ISO goes. And you can get that point. Y'all with me? Okay. You got another one or can I?
I'm good.
Class?
Yeah.
How many here still need to show me your project in MATLAB? 2. Raise your hands if you guys. I got 2, 4, 6. MATLAB project. Then show me your code working. Have you done that? But then you have to, right? You have to do it before 5 today, right? Okay, so 2, 4, 6, 7. All right. After class, I'm going to be there. And remember, if you don't do that, you're not going to pass. Just remember that. I want to be clear, you will fail. So I can't be any clearer, can I? It's not a hard thing. Just show me your code working and you go. And now some of you, I want to tell you this. I told you turn in it before midnight. If I tell you to make some alterations, I'll give you till midnight. I think Jack, you, and didn't I do that to you, Brad? Somebody else?
No.
Who's not here? Oh, okay. Was it you? We got a full complement here? 2, 4, 6, 12, 4. I think we, wait a second. Are we missing someone? I hope not. I have this feeling, maybe they dropped, I hope. Oh, I know, John Bassard. Did he drop? Do you know who he is?
I think, yeah.
Oh yeah, the guy that's over there.
Who's your Wednesday?
Tragic.
He was?
I believe so. Yeah.
Lost soldier.
This is a concerning thing, because sometimes there's stuff going on that is actually more serious than you think. And I've had people involved in all sorts of serious accidents since I've been here. I had one guy that ended up getting killed eventually, but he was in a horrible car wreck. He worked all night. He had 8 o'clock class. After 10 minutes, he used to call him Captain Narcolepsy, trying to encourage him to be awake. I think he got killed in a car wreck. Probably driving, sleepy driving. You know, you don't want to risk your life for the sake of some money. All right. You guys got another one or any other questions related to this? All right. I'm going to go ahead and, yeah.
16.
What'd you say?
He said 16.
16? All right, we'll do it real quick. All these are the same class of problems. Because I need to do stuff with,
He does it 4 ways, I think.
5 all 4 possible.
all right, it's not hard to do, but this means it's outside either one of those, right?
It's
Yeah,
outside
that's
of the
what
top.
I'm saying,
It's outside the rotated and the one circle, the rotated one circle. Now that's the one you want. Because it's got so many different ways to do it.
I haven't been able to figure out, so if you're outside both the circles and you're in the negative J region, you're at the bottom, I haven't figured out, is it possible to even have the shot C element and then the series L?
Want to see it?
Cause
Why
like,
don't we do it?
cause
I'll be right back.
Yeah. But
it is.
I'm going to show you why. Now you got to think in terms of what you can do. Wherever you're at, you're in ZL, right?
Okay.
You don't like ZL, go to YL, right?
Yeah.
Take one over that. So now what do you want to do with YL? Well,
If you're,
you're going to end up going to the rotated circle. Do y'all follow me? You can't go to the one circle. And then you can add, and this, I'm just going to show you.
Oh, so like when it's saying to be able to have a DC bias, that kind of limits the
Selection.
selection. Okay.
And, you know, one thing, you guys are smart. A lot of times, you're just afraid because you didn't do your due diligence and time spent, but, be fearful, but this isn't a good Smith chart, but it's close enough for what we're doing. All right, this is 1016, correct?
Yes.
And we can outline all of them very quickly. And they want an L section, right? What's the characteristic impedance? I assume 50. Is that-
50.
Yeah, that's microwaves, typical microwave stuff. And what is ZL?
20 plus J50.
And, okay. So here's our Smith chart. First thing we get normalized ZL, since it's 50 ohms, that's gonna be what? 0.4, right?
Yep.
Plus J1, correct?
Yep.
All right, now let's locate that. Make sure you can see this. Here's the plus J1 circle right here, basically. Or I'll call it trajectory. And then it's 0.4, I'm gonna say it's about here. I might not be exactly right, but you're gonna see something about here,
Yeah.
and that is ZL equals to 0.4 plus J1. Now take a look at, first make sure you can see that point. You asked about, can you see that point? Okay, you can? That's the first point. Now, what are your options? Remember, this has got a J at 0.1. If we add impedance, which would be adding an inductance, right? Positive inductance, you all follow me? Or, sorry, this is J, I'm sorry. We would have to add a negative impedance, which would be a series capacitor. Out here, you're gonna see these values, this would be like plus J 0.5, and this is an exaggeration, but you get the idea, they're decreasing J numbers this way, right? Please just watch this. Goes to 0. So if we're at J plus 1, we need a minus J, which would be a capacitor in series, right? So it would be a capacitor in series until you got here. Y'all hear me? This is one possible path. This would mean a capacitor in series, right? Just put it down. Now we're here, we go to this circle, and I have 1 minus J something, correct? But that's admittance, isn't it? Y'all follow me?
So
No.
it's shown.
Now we need something with a minus J, or with a plus J admittance, which would be a capacitor. Isn't that right?
Yes.
So what this means is you're gonna have a capacitor. Does he show all these things?
Yes,
All right, so that would be how that would.
that was.
Series and parallel, both capacitors. With me? Now, we could also go. Does everybody understand what I just did and why I did it? Do you see it? All right. Now, what if we do this? I'm going to stay in the impedance domain. All right, Bradley, this is your question. What if I keep adding capacitance and I'm going to add so much that I end up down here, where now I'm got a negative J, or now I'm down to this point, right? Now when I take 1 over that, now I get 1 plus J something. Remember, that's the what? That is the admittance domain. Y'all follow me? I was in the impedance domain, came all the way down here just by adding a series capacitor, but now I go up here, I got a plus J. What do I add?
Inductor.
Yeah, no,
Right, I need minus J, correct? That would be an inductor in parallel. That's a nightmare exam. I mean, that's the worst design, because now this would become an inductor. That's one way. You asked about this. Are you saying this? Or not? Let me ask you this. Do you understand? If I'm here where I entered, that is the impedance domain. That's impedance Z, right? If I'm adding a capacitor, I will have a minus J impedance. I could go to here, right? But I could keep adding a larger capacitor and get it down to here. Do you agree with that?
why?
Because this is gonna have a minus J value, right? We started with a plus J. If we had adding a capacitor, a minus J that was so large, it would not only bring it to here, 0, but it would also bring it down an additional value. Do you see how these are minus J values? Or not? Just go up there and show him. He needs to see that these are, when you get below the equator, these are all negative J's. Do you all see this, class?
Basically, this is the normalized, and you can follow that line down here. That's what we did for the first step.
Show them where the negative J is, though.
But if you continued, it would go all the way down here, and so below this line, these are all negative J values. So negative 0.6, negative 0.7, negative 0.8. So they're positive counterparts up here. So if you go all the way down here, you're in the negative, and that's what he's talking about.
Thank you.
go past the 0, but then you go down to the negative. So it'd be like here.
Now, to answer his question fully, if I'm here, that's still impedance, right? Now I go up here, that is admittance, right? You see it's going to have a plus J component, right? Admittance domain. We don't add a capacitor to that, do we? In the admittance domain, because it would make it more positive. We add an inductor, minus J. So this would take it down there. So that would be, this would be replaced by an inductor. Follow the reasoning. You follow? You asked the question, do you see it or not?
Why is it?
Why what?
Why
Why is it a capacitor from here to here?
in that one, why?
This one? No, it would be an inductor for the second part. This would be an inductor. This is what we did. We added a capacitor here that we could get the value of. Maybe we need to get to here, all right? Just hang on for a second. All right, you follow me on that? Do you know how I went from here to here by adding a capacitor in series? All right, now from here to here, now I have a value that's plus J, don't I? You know why? Because if you looked at the arch, this is a plus J value. Do you all follow me? Now I need to add something on that to that in parallel that'll get rid of it, right? Well, an inductor has an impedance of plus J omega L, right? Normalized, it's plus J omega L over Z naught, right? That is called impedance. 1 over impedance is admittance, right? And it would have minus J. We need to have minus J. That's why there would be an inductor there. How many understand that?
Do you have the textbook open? The textbook?
Go ahead.
Pull up table 10.2.
Just show. How many understand this?
Look at this.
You good with that?
So this is, I don't see what your question is. So this table.
Could
so
you show
in the
solving
example
for
we
the
did
impedance
there.
admittance domain?
Go ahead, say it again.
Could you show solving for the impedance in the admittance domain?
You can't solve for impedance and admittance. You gotta go to the admittance domain.
Right there.
What?
If you're at,
You're talking about right here? Right here?
no, you went up and across.
Yeah, because that's impedance, that 1 over that's admittance.
Could you solve for,
See whether it's.
the value of that inductor?
Yeah, sure. Because how would you get it? You're gonna have a real value for that, right?
Yeah.
You wanna do that one? Why don't we do that one? Let's see, maybe that will help alleviate any concerns. All right, work with me. I need you to help me. Look, here's where we landed first, right? Now we want to get to here, right? Y'all with me? The trajectory on this is 0.4. This has 0.4 real part. Can you find out where it intersects right here? I need this value, 0.4 minus J something. Anyone? Give me a hand with that one. Can you look? Huh?
Whether it's a decrease in J.
Go ahead, Greg, you have it.
0.5.
So this is 0.5. Can anybody verify that? You got that, Greg? All right. Now, you asked that. All right. This is the real, or this is the imaginary part, right? This is the imaginary part we started with. So we went from plus J1 to minus J.5, or we added minus J.6. That better make sense, right? And it's an impedance, correct? So I have minus J, and it's actually going to be plus J, pardon me. Sorry. it's going to be minus J, and it's going to be I went to 1 to 0.5, so I'm going to go from plus J1 to minus J.5, that's 1.5. So I got to have a minus J 1.5. Now, what is that going to be? It's an impedance, it's a capacitor, right? So that's equal to minus J over omega C, but it's normalized Z naught.
I got that.
I'll go the other, I'm going to get this value, then I'll show you how to get the other value. Y'all with me? All right. So that means what? C is equal to what? Well, C is going to be equal to omega Z naught, right? And then it's going to be divided by 1.5, 1 over that. Do you all agree with that? Give me a value for that. What's the frequency for this one?
2.5 gigahertz.
2.5 gigahertz. All right, so give me the Z naught is 50, so give me the value for this capacitor. I'll call it C1, and this will be C1.
That's a capacitor.
What happened?
Charger. For this guy.
Oh, you need, no, sorry, go ahead.
Series capacitor
Yes.
is going.
Anybody can do the calculation for me? What do you got?
0.85 pico.
That's getting down to the lower limit of what I feel comfortable with. All right, so that's C1.
Where did that 1.5 come from?
All right, hey, look, if I start here, just look, right? I'm at J1.
Gotcha.
I have to get down to minus 0.5, that's a difference of 1.5, it's negative. Okay, now, next, I'm here. This value is 0.4 minus J.5, help me with this. 1 over that will land me here, but I need the J value.
1.2.
Confirm it, anyone?
Yeah.
1.2. We need to get rid of that. We're in the admittance domain. So I know it's going to be an inductor. All right. So for an inductor, inductive reactance is J omega L. Do you agree? Normalize it, divide by Z naught. That's normalized, right? But that's the inductance, and it would be ZL. It's a normalized inductive impedance. 1 over that, or YL, is 1 over ZL. And that's going to be what? Minus J Z naught over omega L. What's that value? That's what you're asking about. Thank you. Anytime you can help somebody, do it.
And just to be clear, you almost never want that, right?
No, I don't. I'm going to say this, though, Wentworth does. No, I mean, I'm talking about realistic designs.
I don't mean like in a problem, I just mean like, yeah, realistic.
If you're building stuff, that's a brain dead kind of mistake. Because now, I mean, if you're going to do any kind of repetitive design work with that thing, if you got to bias something in DC, and by the way, in general, capacitors in parallel kill noise. Inductors in parallel, they look like antennas. I mean, it's not quite an antenna, it's a near field coupling device. You don't want that. I'm just telling you, it's personal from all the pain I've suffered with all the crazy stuff I've seen.
Those are good for biased T networks, though.
What?
The inductor, if you have an inductor that has a DC going to it, and then a capacitor and series.
Usually you have inductor, a T is a capacitor to ground, and then another inductor.
Yeah.
All right, what do you get for this?
2.65 nano henries.
Oh, let me get rid of that. So that's going to be, L is 2.65 nanohenries. Anybody confirm that?
Yes. Right.
All right, and that would be the value of L here. And that would work, but I wouldn't recommend it. All right. Now, that's 2 of the 4, right? What else could you do? I come in here, that's ZL. What if I don't like ZL?
Go to the admittance.
I go straight to the admittance domain, right? You are, now you can see there are two ways to go. Now look, well, no, I'll say there's 2 points. Here's the trajectory, right? For the real part of this is something like this. I'm trying to show you this. This is not going to be very good, but you get the idea. You got a real part here. Don't worry about it yet. So I can hit what? I can hit here, and I can hit here, right? That's admittance, right? So I can hit here, or I can hit here. Admittance. Now, if I go here in the admittance domain, when I go here in the impedance domain, I'm going to have 1 minus J something, right? Impedance. I would have to add an inductor, right? In series. If I go here and go here, then I'd add a capacitor in series. Y'all follow me? And that's the reasoning you go through. And you don't, the basic thing is just take a moment, think logically about it, and it makes sense. You should see this. There comes a point when you just see this stuff. Usually. Good with that? All right. So I want to do a couple things with S parameters now, unless you have another question. Most of this is very obvious and straightforward if you work the problems. Take some time. I always recommend at least an hour or two between class periods to do the problems and understand it so you can move on. And if you have an understanding of what I've covered, the next stuff usually builds logically. Otherwise, sometimes you are just so lost you don't know what to ask. Which is, I felt that way before in these short courses where they do like 5 or 6 hours straight lecture without giving you any problems to work or anything like that. By the end of the lectures, why are we here? All right. Did anybody do any of the S parameter problems? There will be S parameters on the test, on the final. I hope you did. Some of you have had S parameters before. They're used everywhere. As a matter of fact, I'll have to say this. When you go through a job in the real world and you're doing anything high frequency, microwave, antenna design, radar, any kind of comm link, S parameters, you're going to be working in that domain. So the best way for me to do is start with one very simple one and move from there, all right? So I gave you some problems to do. Did anybody look at them? Did you try it? Well, I appreciate honesty. I had one German professor. My God, that guy would have nearly killed me if he didn't do his homework. I got called a Dummkopf on there once. I'll never forget that guy. He was an incredible teacher, but man, intolerant. If you did not perform at the highest standard, you were an idiot. Why are you even here? Get out of here. They would have shot you back in the neck. Failure was not an option. Death was. Not failure. The guy's name was Feuchtwanger. I'll never forget it.
Where was that? An American?
From Germany. He was Jewish. He fought in the Israeli wars. He came here. Talk about an asthma. He had zero tolerance for anybody who didn't do everything he was asked. And there was no forgiveness. There was death. Okay. So I gave you a bunch of problems that were really simple. This is problem 1024. I hope you get a chance to look at them. If you don't look at those, you really won't stand a chance on the final. I'm going to take a look at problem 1025. So now this is, I'm going to build. This is a classic problem. It's the beginning, the simplest possible problem. From that, if you understand it, the next several steps will make perfect sense if you understand this. So here we got a characteristic impedance of Z naught here. And then we got a resistor R. And it's put in, this is a transmission line. This is a very short wire with resistance R. And then here's the other transmission line that has the same characteristic impedance. Now, this is port 1, and this is port 2. You've got an incoming signal here. It's always designated, this is port 1, so if it's going into the port or into the S parameter, into the, what do you want to call it, the device, this is S parameters for this, it's plus. If it's coming out, it's minus, so it's V1 minus. Here, you're going to have a V1 plus and a V1 minus. Are you with me? That's just standard. And these are propagating waves. There's a propagating wave going in, a propagating wave coming out, a propagating wave coming in. I mean V2, pardon. This should be V2. I'm sorry about that. Do you follow the trend on this? There could be more than that. There can be N ports. We could have V3 coming in, V3 going out. V3 plus coming in, V3 minus. There can be 3 ports, 4 ports, N ports. This is just the simplest possible thing. So if you look at what V1 minus is defined as, it's S11 times V1 plus S12 times V2 plus, and then V2 minus is equal to S21 times V1 plus S22 times V2 plus. Now that's the definition of the outgoing signals from either port based on the incoming. I want to make clear on that, all right? Now, when you want S11, S sub 11, that's equal to V1 minus over V1 plus, and it says V2 plus equals 0. Let me tell you what that means in a simple sense. So what does V2 plus equals 0 really mean? Here's what it means. It means this transmission line goes on forever, or you can think of it into a matched load, so there are no reflections. Do you all with me on this, class? So it means the signal gets through, it goes out, and never reflects back. You can either think of it as an infinitely long transmission line or transmission line terminated in Z0. Follow me on this, guys? All right, so we need to find S11. That's the reflection coefficient, isn't it? Does that make sense? Now, what is the reflection coefficient for this? First, I have to show you the equivalent circuit. From this end, what it really looks like, looking this way, here I have a transmission line with a characteristic impedance of Z0. Then I have a resistor R, but that's in series with another transmission line with characteristic impedance Z0. Does everybody understand that? So this really looks like I'm going into a load of R, and I can put it plus Z0. Might as well just show it that way. Where this is where the end of port 1 is, right there. So what would the reflection coefficient be at that port? Well, it's the impedance you're going into, R plus Z0, minus the impedance you're coming from, over the sum of the two, which would be what? R plus 2Z0. First, does everybody agree with that? Y'all with me? This reflection coefficient. Impedance you're going into, minus the impedance you came from, over the sum of the two. So this one really is just going to be R over R plus 2Z0. And by the way, what is the value for R for this one? 50 or something? I don't know. Can you tell me if this is going to be problem?
50 LT line and certainly.
What is the number on this one? 10.25?
Yeah, 50 ohm resistor followed by shunt, 50 ohm.
No. This is just one. I'm hoping it's one, but it's not. I want to do it as simple as possible. Oh, we're going to do 50 ohms first. We'll put the shunt later, all right? I'll do it right after this, but I want to cover it. So follow me. If this, forget the shunt right now, it means it's going to have a shunt over here. But what is this going to be? It's 50, right? Sorry, 50 over 50 plus, and Z0 is 50? I hope. Right?
Yes.
But it's times 2. So that's gonna be what, 50 over 150 or 1/3? Y'all follow me on that? Now, for this particular one, do you see how looking at this system from this side or looking at it from this side, it looks the same? You have a resistor in series with the other transmission line, same impedances. Y'all with me? That means if you've got S11, and we do, which is 1/3, we also have S22 from arguments of symmetry. That should be clear. Does that make sense? There's a formal definition. This is the easiest thing. Just look with your eyes. It looks the same one way as the other. That's all you need to do. And by the way, if it had a resistor here and here, same value, it would still, if you got S11, it would still be S22. Y'all follow me? It's a symmetric system. So anyway, get rid of that. Now that after that, we have S11 and S22. Now we need S21. S21 is going to be V2 minus over V1 plus. Now, this is important, you see this. All right? I want you to follow this. I got a wave coming in, right? I know I have a reflection coefficient here, right? Y'all with me? So the reflection coefficient here in port 1, that was equal to what?
1/3.
1/3. You all follow me on that, everybody? That means the transmission coefficient in port 1 is going to be what?
1 plus 1/3.
Right? Isn't that right? You all follow me? So that's what? 4/3. Do y'all follow me? Now watch this. So a signal comes in, V1's coming in, some of it's reflected, some of it is transmitted. Please watch. How much is actually transmitted? Well, the transmission coefficient says that the transmitted signal that's just beyond where that transmission line is attached to those wires will require that the signal that's transmitted right here be tau, the transmission coefficient, times V1 plus. Do y'all see that? This is very important. Are you good with that? So when I draw this, I can say, if I look at this, I have a signal V1 plus going in this direction. Then I have that resistance. And then I have another characteristic impedance of Z0. I know between here and here, I have V1 plus times 4/3. That's the voltage between here and here. Do you all see that? Now after that, this looks like a simple voltage divider. Does everybody see that? I want this voltage right here because that's the voltage that's going to propagate out. It's just the voltage developed across Z0. So I can say that this V2 minus is equal to, start with this voltage, which is 4/3 V1 plus, and then use simple voltage division, which would be Z0 over Z0 plus R. Does that make sense to everybody?
You said that was V2 minus?
Well, when it
Across
flows
Z0.
out, remember, going out of the port is minus, into the port is plus. So it's V2 minus is going to be the voltage developed across Z0. Y'all see that? Which is the equivalent impedance that's at this port, looking that way, Z0. Y'all see that? So what is this going to be? Well, let's see, V2 minus is equal to 4/3, let's do this. V1 plus, and then what is Z0? 50, right? Over 50 plus 50 or 100. Can you all see that that's going to be equal to, that's 1/2, so it's going to be 2/3. Better write this thing right. V2 minus is going to be 2/3 times V1 plus, right? Can you all see this? That means what? When I look at S21, it's V2 minus, well, V2 minus in terms of V1 plus is gonna be 2/3 V1 plus. So it's 2/3 V1 plus divided by V1 plus, or just 2/3. You all see this, class? If you didn't do them, I know some of the stuff can seem a little daunting, but you'll get it. And the S matrix for this would therefore look like, well, S11 and S22 are both 1/3 and 1/3, right? And then S23 is 2/3, and S21 is 2/3, and S12 is 2/3. It's a symmetric system. You all see the diagonal is symmetric both ways. You all with me? And that's what the S parameters would be. Now, if he puts a resistor here, and I'm going to talk my way through this. I want you guys to, if this is 50 ohms, here's what changes. Please listen. Now my input impedance here changes. I have 50 in parallel with 50, which is going to be 25, right? 25 plus 50 is 75. Now my input impedance is 75. With me? Now the reflection coefficient that I had here is going to be different. Now it's going to be, think about it, going this way, it's going to be 75. So 75 minus 50 is 25, right? Over, and this is going to be 75 plus 50 is 125. So now it's going to be 125, or sorry, 25 over 125, which is 1/5. Y'all follow me on that? So now that changes the input impedance, that changes the reflection coefficient. Transmission coefficient also changes, right? Now 1 plus the reflection coefficient is going to be what? 6/5. Do y'all follow me? So now that changes, and that will change the S22 parameter as well as S11 and S21 and S22. Please do those problems. They're laid out in the book. And you can consider this, that everything else boils down to this. If you want S parameters, you find the input impedance on either port. They can be quite different. From that input impedance, you get the reflection coefficient. From the reflection coefficient, you go ahead and find out, the reflection coefficient basically gives you S11 here. You get S22 by just looking at this from the second port and doing the same thing. Then you get the transmission coefficient and do voltage division. All right, I'm going to have to give you a quiz, so let's do it this way. How about you populate this row? Let's populate that first row, because that way all these desks are split together. And then everybody behind Keenan here.